I still haven't fixed my intro. Um, that's the best I got, I guess, for now. But I need a new one.
All right, hi ICBers again. So what we are doing right now is we are trying to dial in to the first lab of the year. So by now you've finished your safety quiz and your safety contract is turned in. And what we would normally do is we'd go ahead and take a look at the lab. Now, obviously we're not in person, so we're going to kind of walk through this lab together. So here's what I'm going to do. I'm going to click on it. It's going to open this up for me so I can kind of see, where it's taking me through. And I'm just going to kind of run this lab through with you guys today. There's a couple parts on here I'll sort of show you like how I would answer this, things I would do. But before I do anything, I'm gonna do file, make a copy, because I want to actually access this and type my stuff directly in there. Now, where you guys put this as far as your folder is concerned, I mean, that's up to you. I would probably just make an ICB1 folder because we're gonna do labs like this all the time, where we can just edit the actual document and have it almost as our notes. So I'm just gonna kind of throw it into this random folder, so don't worry too much about it for me. But then with this copy, I can essentially make this video and type directly in here and be good to go. Okay, so let's run through this together and see what we're trying to look at. Now, if you remember, we had a discussion about fire, and we're sort of shifting gears here to try and talk about more of a thermal energy rather than a fire. Okay, so that's fine. Um, let's see what this particular thing is asking us to do. So, by purpose of intro, have you ever left a metal spoon on a pot on a stove and tried to pick up the spoon with your bare hands? Ouch! Why does the metal spoon get so hot, but a wooden spoon does not? Why does a marshmallow burn when it's held over a flame, but only gets toasted when it's next to the flame? These questions involve the same principle, the transfer of heat. Now, our background, in order to truly understand the process of heat transfer, we need to define a couple of terms related to thermal energy. So I'm going to kind of do that for us, which, isn't great practice as a teacher, but honestly, I'm trying to do the best we can with this remote process. So if we talk conduction, conduction is this idea of the ability to transfer energy via direct contact. Sorry. So if we touch something hot directly with our hand and transfer that heat onto our hand, that's an example of a conduction transfer. Now, when we talk about what thermal equilibrium means, thermal, of course, for us is going to be heat. Now, I'm going to say that in quotes because heat for us is going to mean a lot of things this year. So I'm just going to make this kind of a generalized idea for us off the get-go. Now, thermal equilibrium means the heat on both sides of a system barrier are essentially equal. Okay, that's a lot. So I like to use the example of ergo ice cube melts in water, now have cool water. So once we get to the cool water, we don't have that original water at that starting temperature. We don't have the ice at its starting temperature. Those two have sort of mixed together. Heat has flowed from hot to less hot. In this case, the heat from the water went into the ice cube. And we've reached a new equilibrium where it's just one system now. The barrier has sort of been eroded. All right, thermal conductivity. So with thermal conductivity, that's sort of the ability to transfer heat. And it's honestly sort of an inherent sort of physical property related to the object. And so some objects are much better at transferring heat than others. For example, metals. Metals are very, very good transfers of heat. They're usually not very good storers of heat because of that as well. However, sometimes that can change as we start talking further. Convection. So you may have heard this term as related to stars or just an oven. Convection is a flow of heat, and it can be liquid or gas, usually. You can have solid, but that'd be talking more about the idea of the earth and sort of in the upper mantle, and that's a little bit confusing, but it's the flow of heat in a cycle. And the cycle would mean, and you've heard this before, warm rises, less warm sinks or sort of goes down. And we'll talk about what this cycle looks like specifically in this lab here in a second. Last but not least is radiation. And radiation is the transfer of energy via, for us, we're going to say via light. Now, it doesn't have to be, but essentially it's contactless. You have some way, one way or another, you're transferring energy, you're radiating it outward from one spot to the next. Okay, These aren't perfect Googleable definitions, but it's good enough for us to work with. So let's see what we're actually trying to do. All right, the goal of this activity is to use stations to demonstrate different methods of heat transfer by conduction, convection of a liquid, convection of a gas, and radiation. Conclusions will be made from the observations of each method. So you want to start by reading over the experiment and creating a blank data table that's easily filled in as you go along with the lab setting. There's a couple analysis questions to answer at your data table once the experiment's been completed. Okay, so I'm going to sort of hold off on the data table right now, and I'm probably just going to type my data directly into this document just because we're doing this remote. It's a little bit different. All right, so station 1, conduction. So some materials conduct heat better than others. In part 1, we're going to compare the thermal conductivity of two materials by you using your sense of touch. Metals are generally considered to be good conductors of heat. Do all metals conduct heat the exact same rate? In part 2, compare the thermal conductivity of three different metals. Okay, so we obtain a plastic spoon, and I'm going to go ahead and sort of just place it onto my hand. And then you would take a copper metal strip and you sort of lay them side by side. Now, I don't have a copper metal strip at home, but I have a penny. And so that's starting to alter the contact zones. Maybe I'll use a couple pennies. If you touch the spoon, the plastic spoon, you're not going to feel that it is actually, feeling cold to you. It's just going to feel like a plastic spoon. Yet when you actually touch the copper, or really any metal of this particular situation, is going to feel cold to you. Now that's weird because both the plastic spoon and the copper are at the exact same temperature, room temperature. But for some reason, the copper feels cold. And that's odd, unless you think about what transfer means in terms of conduction. So if you remember, conduction is the transfer of thermal energy, or the ability to transfer energy via direct contact. So you are warmer than room temperature. You are a warm-blooded animal, and so you're going to be sending a lot of heat outward. So what's actually happening is the copper is siphoning your heat. So when I record my observations on here, I'm probably just going to say something simplistic like, hey, the spoon felt like plastic. I mean, this is a terrible observation, but it's just kind of giving us a ramification. The copper felt cold to the touch. And I'm not asking you to do rocket science here. We're just kind of filling a spoon in a piece of copper. Like, that's it. And then this is where it would be more fun in lab together because we actually get three different strips. And so we'd use aluminum, copper, and zinc strips. We would mark these with a little line, and we'd put a little piece of wax onto the copper, the zinc, and the aluminum, and we'd throw them into some nice warm water. Now we'd start a timer, and we'd see the time it takes for the wax to melt on the copper, the zinc, and the aluminum. And what you'll see is that each one of them melts at a specifically different time. I'm going to provide you with some of that data there at the end here so you can kind of see it. But what that would mean is each one of these strips is conducting heat at a different rate. And so you'll find that aluminum and copper conduct much faster than zinc does. So if you were looking for a very strong conductor of heat, or something that has a very high conductivity, you'd use things like copper and aluminum, which happens to be the reason why a lot of fancy cookware is made from copper, because it is extremely good at controlling heat. Some of the less fancy cookware is usually made of a combination of steel, which does have some zinc inside of it. It's just a little bit cheaper than trying to make a bunch of cookware out of copper. Aluminum is still pretty good at conducting heat. It's better than zinc. It's not quite as good as copper. And so what we should see from these metal strips, and I'll just jot this observation down sort of as I'm going, is the copper melts the wax first, and you'd have some arbitrary time in there. Let's just say 5.2 seconds. The aluminum melts second, and we'll call that like 7.3 seconds, just making up some data. And the zinc melts last. Now, this would be significantly longer. This would be closer to around like 14.2 seconds. So we'd wait a while for the zinc to actually melt that wax bead down. But this data is going to help us answer some questions later on. All right, on to station 2. So station 2 always takes a while because station 2, we usually set this up in the class, and you have this 125 milliliter Erlenmeyer flask. It's got some red food coloring inside of it, and I place it sort of confusing looking where we've got one tube at the top and one tube into the container, and I have different kinds of temperatures of water. So usually I'll heat up this red water of the Erlenmeyer flask inside of it, and I'll place it in some room temperature water on the outside. And then what I usually end up doing, and what you'll end up seeing on here, is I'll take a time-lapse video. Now, what happens is the red material spews out into the outside, into the less warm water. And the observations we see to kind of record into our data table is that um, so let me get to the text here. Here we go. The red water flows outward from the warm flask. The colorless water flows inward from the less warm beaker. And it's strange to see, and you might want to sort of stop the video and kind of replay it over again, because it's hard to actually watch this take place. Because you'll see this red stuff sort of come out, and then if you look really close on here, you can actually see the colorless liquid sort of siphoning its way into the flask. And this will happen until we reach thermal equilibrium, where essentially the amount of heat in both sides is the same. And consequently, because of that, the temperature will end up being the same. But we want to be careful because temperature is not the same thing as heat. And we'll get to that much, much later in the year. This one's more my favorite one, though, with Station 3. So in Station 3, you have a birthday candle. We usually put it on like a piece of Play-Doh and have some water. Okay, we light the candle and we just watch the candle burn. Okay, but it's also the first time I can get you guys to light something in class and you have fun and it's safe and we are all okay. And so then you take this cylinder, and what happens is the cylinder, when you put it above the candle, not with this T-shaped thing inside of it just yet, the cylinder will actually blow the candle out. Now, that makes sense if we think about our needs of fire, because as we have this cylinder sitting on top, it is actually open at the top, but the flame sitting down here on the candle, it will eat up the oxygen too fast for it actually to be replenished. The oxygen can't flow in because all of the hot material is sort of leaving the top. And so the candle will self-extinguish itself, self-extinguish. What's really weird though is if we do this again, and now we take a T-shaped divider, and I'm showing you sort of this image on here to kind of help you out to see this. The T-shaped divider will allow the material to start making convection flow or a convection current. And what starts to happen is the warm material will rise up one side of the T, and the cooler air will kind of sink down and keep the candle going. And so the candle won't go out. This is actually really cool to see in class because it's sort of mind-blowing to see that, well, why did it go out the first time but not the second? And you can actually place your hands on the side of it and feel that one side of the T is actually much warmer than the other. So it tells you to do all this stuff with seconds and everything else on there, and it's fine. Like what you end up seeing is that, okay, the material is flowing up to the side on one and then flowing down on the other. Okay. The last one we look at is I take a heat lamp and I place it next to some white sand and some black sand. And this is so obvious that you guys don't have to even do it. And so often what I do is I just sort of attach a graph so you can see the temperature changes over time. And no surprise, the black sand rises in temperature much faster than the white sand does because of its absorption and its ability to sort of take in that initial heat versus the white sand, which is reflecting more of the light. The only reason why this one's actually included is because radiation is very hard to actually show you guys this mode of thermal energy transfer, and this is sort of the easiest way to do it. Okay, so now we've got all this data, we've kind of walked through it. What's our analysis questions actually say? So, Station 1, so that was where we touched the plastic spoon and the copper, and then we had the different strips of metal on there, and we kind of looked at it. We said, using our data from part 2, rank the 3 metals in increasing thermal conductivities. And so that's pretty easy. We saw the copper, melted the wax the furthest. So we want increasing thermal conductivity. So the worst one was zinc, which was, the slowest to actually melt the wax. Then aluminum was second, and copper was the best. Now, using the data table below, predict when you would have expected the wax to melt on a strip of iron. Okay, so here's copper. It has a thermal conductivity of 4. I don't really know what all this stuff means just yet, but it's not super important for us just yet. We have aluminum, which is 2.4, and then we've got zinc, which is 1.2. So copper is the fastest, then aluminum was second, and zinc was 1.2. Okay, iron. That's what it's asking us, right? So iron's kind of sitting right here. It's only 0.7. So almost about half of what zinc is. And if you remember way back when I made up the data about that first part, we said zinc took 14.2 seconds. So my guess is if it only has half the thermal capacity, or thermal conductivity in this case, let's say, I don't know, iron, probably going to melt, oops, going to melt the wax around a time of 28 seconds, or about double what we saw from everything else, because its thermal conductivity is half that of the zinc. Now, it's not perfect, but it would at least be something we could test. And if we had class time together and face to face, we'd go back there and we would test this thing out. So we could see, is the iron actually matching what we expect it to be? All right. So in station 2, we had that flask with the Erlenmeyer, and we had the red water sitting inside there with that video. And it's asking this question: if the flask and the beaker setup were left longer period of time, would the convection of the water eventually stop? So would the convection stop? That's sort of a tricky question. So sort of. You would see no net changes. Now, net changes mean we're not going to see no more warm water coming out and cool water coming in. But we would still see some transfer of water. And the reason for that is when you reach equilibrium, materials don't stop moving. It's just that for every one that goes out, one comes in. So equilibrium just means no net change. However, materials are still moving. So when we ask, is convection stopping? I guess so, because convection is sort of about a net movement. We're having the warm rise and the cool fall, or go one way or the other. And so it asks you to draw out a diagram from the station, use the words hot and cold with some arrows so you can kind of see it. Um, Great, yeah, I've sort of provided one for you here so you can see sort of how I would dial this in so you guys could see it. I have no doubt you guys could draw some arrows going outward from the flask and sort of coming inward from the beaker. All right, so explain the purpose of the divider and the cylinder. All right, so that was the station where we had the lit candle and we saw it go out with the cylinder, and then the divider, the aluminum T. So the divider, for our purposes, is setting up a barrier. So the divider is essentially our barrier to allow for convection of a gas. Okay, draw out and label the diagram of the station using the words hot and cold. And so again, I provided you another picture so you guys can essentially see, okay, the warm air is rising on the one side and the cooler, less warm air is sinking in from the other, allowing a net influx of oxygen so the flames sort of can still stay going on there. And then lastly on here, explain what is meant by when something is heated by radiation versus convection. So the biggest difference with radiation is that when we talk via radiation, we are essentially saying contactless. In other words, not touching. This is confusing because it's hard to imagine why energy would transfer without something actually coming into contact. And the short answer to that is it's usually involving light, and it's usually involving materials that are traveling over a long distance. Think for the sun. The sun radiates the earth. Then the earth also does have conduction and convection currents as well. So it becomes very, very almost like a large system of all different ways in which heat is being transferred, where the heat origin is the sun, at least at the surface. Below the surface, we have a heat origin of our core. So there's a lot happening with heat flow as we start talking about the Earth in general. And so when it asks you finally at the end, graph the black and white sand using a best fit line, pieces of data, okay, be sure to label the axes. So I already provided this for you. You don't have to do this. But what you want to notice is that the slope is different. The black sand has a much higher slope, meaning it's warming faster. Its temperature is increasing faster. So it has some sort of ability, since they're the exact same mass and same particles essentially, to sort of absorb that heat faster than the white sand can. And you can sort of imagine why, because the black is much better at sort of holding that in place, or sort of holding the energy. Okay, that's a real quick overview of this lab. It's sort of a process. You're going to probably have to rewatch this a couple times just to make some sense out of it. But for the most part, that's what we would have done in class kind of together. Some of these other labs that are a little bit more confusing, you'll actually see me doing them hands-on rather than just showing you some clips.